Okay, does everyone see Dr. Rackett?
Yes.
Yes.
Yep.
Right. So I think what I'm going to do today is essentially the same thing that I did last Monday, which is reveal part of the solution to an assignment and explain what I think the takeaway should have been for those who haven't finished the assignment yet and for those who have finished it. So does anyone have any questions first? Right. Most importantly, we're going to have a midterm. And this is going to happen next Tuesday-ish. Meaning 24 or 36 hours. It depends on what people's time zones are. I'm trying to coordinate that with some people between lectures. And this is a very good way to ensure that everyone gets caught up with the homework. Conceptually. I think conceptually is the key point. None of the problems are going to be direct modifications of the homework problems, but they're going to use the concepts that were required to solve the homework problems. So for example, last Monday, I explained retrospectively upon looking at solutions, some proof principles. And this time I'm going to explain some principles about how to develop programs. So this is very much the key point conceptually in terms of problem solving strategies. So I'm going to discuss half of the implementation of unique left. And then still submit this late, less credits. Okay, so first off, I want to like this. So I'll do an example first. This is how I would like you to write all of your Racket functions. Let's consider the function SUMList. So every single function that you write, when done in the proper style of thinking through the problem, should begin with 3 lines of header as a comment explaining what the function does, its name, and it's what I'm going to call its signature. So the first line, I'll write the name of the function as a comment. On the second line, I'm going to write the signature of a function. In other words, what types of things does it input and what type of thing does it output? So what does SUMList take as an argument?
A list?
Of what?
A list of elements?
So,
I mean, specifically numbers. Yeah.
Yes. I'm going to, by the way, change the notation because it'll be relevant for a homework that's due this week. Instead of, so this is a retcon. Instead of writing list of numbers, I will write I want to write it as a single word. So I'll write list and then I'll put angle brackets, less than and a greater than sign, and put number in here. So this means list of number. It's a list whose elements are numbers. So SUMList takes a list of numbers, and what does it give?
A number.
It gives
A number.
A number. Now, the third line is perhaps the most important line in this preamble. You need to describe, so there's a difference. Let me start with this. There is a difference between the definition of a function, the code that actually defines it and says how the function computes, and a mathematical description of what it is that the function outputs. So for example, we gave two implementations of SUMList, one with an accumulator, one without an accumulator. We also gave two implementations of reverse. Now, all of those implementations, well, each of those two implementations, produced the same output for every single possible input, despite the fact that the functions had different definitions. But that's because both functions solved the same problem that can be described mathematically and logically. It doesn't, a description of what the function does, not literally, but abstractly, what's its purpose, what goal does it serve, that doesn't refer to actual actions that the function does. You just say, when you call SUMList on a list of numbers, what it returns is something, and that something is some abstract description of what the output is in terms of the input. So what's a good description for what SUMList does? Not literally, but abstractly.
It sums the first number in the list to the sum of the rest of the
No,
numbers in the list.
that's literal. That is literal description of what the actual function does. But that's not what what purpose the function serves.
It just sums all the elements of the list.
Yes. So like Martin, the description that you gave would also apply to SUMList 2 equally, sorry, it would apply to SUMList, but not SUMList 2. But we want some description that just says what it does. So when I say a function outputs something, I'll say returns. And then a number returns the sum of the elements. And then I could write of the input lists, but I won't write of the input list. I'll write of LST. So in the description, I will refer to the parameters in the function. So here's the function, SUMList. It takes one parameter, LST. Then before I even write what the function is, what do these three lines above tell me? They tell me, first off, this is a description of the function SUMList. What does SUMList take? It takes a list of numbers. What does it return? A number. What is that number? Well, that number, what it returns, is the sum of the elements of LST, which is the parameter that's passed to SUMList. So if you actually just look at these four lines right here with the ellipsis, then those four lines should define what the output of SUMList is, completely independently of how it's implemented. No matter how you implement it, if it does what the third line says that it does, then it will solve the problem of summing the elements in a list. So that's one distinction that I'd like to draw. There's a difference between the literal implementation of a function and the definition of the problem that it solves. And it's very important, as you'll see when working out how to write a problem, to understand what the description is of the abstract problem that it is solving. So that's vague. It's made concrete by going through examples. But does anyone have any questions about that? No? Okay, well, so now, okay, so this is an example of how to develop this function. So I'm showing you right now the problem-solving methodology that you should use. Well, if I look at this function signature, what it takes is a list of numbers. And in general, when I have functions that take lists of numbers and need to process them, I should start, and I would like to write the function in a structurally recursive way. The way that you start right away is just with the template for a structurally recursive function taking a list parameter. And then what's the second case of the template? What do I write after this bracket if I'm just writing the template? Anyone?
Else.
Okay,
Then
then
do something to the first of the list.
and
Then some list the rest of the list.
yes. So here, the order of these two doesn't matter, and I don't even have to use first list, for example. What does matter is that this case says that somehow I need to combine the information of some list rest list with the information of what the first of the list is to obtain the sum list of the list, which I'll explain in a second. So this is how you always start by doing a problem. You start by giving a name to the function that you're writing down its signature. Its signature is a very basic property of the function. So for example, this function returns a number. If this function instead had to return a list, that would be a very different class of function. A function that returns a number is very different from a function that returns a list in the way that, for example, you'd write it and think about it as well. And then you need to know what problem it is that you're solving. And so the third line is perhaps the most important line of the preamble because it forces you to write down a concrete description of the problem that you're trying to solve. And we'll see why this is really important. So if you have an empty list, now you start filling in the template. If you have an empty list, what should the sum list of it be?
Zero?
Yes. The empty sum is 0. Now, instead of filling in this template, I want to show you what it is that we're really thinking about. So first off, let's say I take the sum list of lists 1, 2, 3. What should the output be?
Six.
Right. Now, let's say I take the sum list. Here we are. I'll take the sum list of, I'll add 5 onto the front of this list. Now, what should its output be? So 11 is right, but it's right only technically. What should the output be in terms of 6?
6 plus 5.
Yes. I'll put 5 first. 5 plus 6. So when I've added 5 to the front of the list, the way that the answer changes is that I add that to the answer. And in general, if I look at a more general case, let's say I have sum list LST, just LST. I don't know what it is. And then I instead consider sum list cons, elements onto LST. So how can I describe this in terms of SUMList, LST, and ELT?
Plus element with SUMList LST.
Yeah. Now, in general, remember that in our particular case, when we're filling in the templates, if LST is not empty, then always. If I take any list that's not empty, so I can take its first and its rest, if I cons on the first element of the list to the rest of the list, then this is equal to list. So this is something that holds for every single non-empty list. So as an example, let's say I take list 1, 2, 3. And let's take, I take its first elements. And then I also take the rest of that list. So first off, what is its first elements? It's 1, right? Now let's say I take the rest of the list. It's list 2, 3. And now what happens if I cons on the first of that list to the rest of that list? I get the original list, right? This doesn't work for the empty list. What would happen if I tried this on the empty list?
Get an error?
Which? What would the error
Not
be?
sure.
Well, why would it give an error specifically?
Well,
What's the problem?
I think it would be okay with the first of the empty list, but not the rest.
What is the first of the empty list?
There needs to be at least one element for there to be a first.
Yes.
So I guess neither.
There's no meaningful answer. So yeah, if this will get evaluated first and this will throw an error, this would also throw an error if it got to evaluating the rest of the empty list. Also, here's another reason why this has to fail. A list is either empty or cons of something onto a list, right? And those two variants are distinct. So this can't be the empty list because this is a cons. And a cons is always distinct from an empty list, right? Well, like we see that this operation is always returns the original list if the list is not empty. That statement can't be true for the empty list because the empty list is never a cons. Does that make sense?
Yeah.
Okay. Anyway, so the reason that I went through that digression is because here I asked what's the relationship of lists, some list of LST to some list of the list const and element on the front. And we said that the relationship was you take the previous answer and you add elements. Well, when you're doing structural recursion, it's really the same thing. What you have is some list of rest of LST. So you have this, and you want some list of LST. Because after all, what are you doing? You're literally defining what some list LST is, right? But you're assuming that you know what some list of the rest of the list is, as though it were a proof by structural induction. But what you know is that list, this is the same as what we had before. So really, you're just solving this problem. how do I go from knowing the sum list of a list to knowing sum list of cons and elements ahead of it? Because you know sum list rest list, and you want sum list cons first list rest list. And so, okay, does everyone see that? This is an incredibly important point. If you don't understand this point and you don't ask a follow-up question, I'll be sad. Like, I expect you to ask a follow-up question if anything is unclear. This is a crucial thing. Okay, so moving on. So how do I fill in this template now that we figured out how to go from knowing sum list to knowing sum list cons something onto it? So how do I complete this template?
So you could say else plus first list with sum list rest list.
Yes. So you take your previous answer, and the way that I've bracketed it already, it's already good. Oh, by the way, here's a cool trick. Notice how, okay, so let's say I'm closing brackets. This bracket is a square bracket, right? I'm just going to press the button for closing parenthesis. So I press the parenthesis close button, it closes with a parenthesis. I press the parenthesis button again, it closes with a square bracket. So you don't have to type a closing square bracket. You can just type in a closing parenthesis and it'll choose the correct type of bracket. And also, if I just keep pressing it right now, so I'm pressing close parenthesis right now. Okay, never mind. Ignore that. Okay, now I need to tell you another very important thing. Marmoset has limited release tests because it's possible to test the problem on your own. And one way that you can test it is you can write statements like equal sum list 1, 2, 3, and 6. So if your function is implemented correctly, this expression should return true, right? And if it doesn't return true, then you can be 100% certain that you've made a mistake. And let's try another case, just to be sure. No, well, I mean, it doesn't give us absolute certainty, but let's also test that sum list of the empty list is 0. So these are two tests. I'm now going to comment out all of these lines that I used to think about it. And now if I run the program, it'll output true and true. Now, when you submit your code, I'd like you to remove all of these test lines because they produce output. But there's another thing that you can do. Instead of saying equal to run a test, you can type in the line test expects. And then if you press run, okay, there is a spelling error, is there? One second. Oh, check, sorry, check expect. Thank you. And this won't produce expressions in blue, but you'll just see a purple line saying that the test passed. And then let's say I would write something like 1, in which case when I ran this, well, you don't see it right now, but there's another window that opened up. Do you see this window right now? A different window.
No.
Okay. So it opens in the same way that the stepper opens. Right now it says ran 2 tests. One of the 2 tests failed, and then it tells me what the failed test is and where it failed. So on the other hand, if your tests passed, then it wouldn't produce an output expression. It would do something called printing, and Marmoset ignores things that your program prints. So in other words, you can leave check expect statements in when you submit your code. So generally, when you write code, after you write any function, not just the function that you're trying to solve, any function, you should put some check expect statements to see that your code actually does what you expect that it does. So here, we've gone through the development of the SUMList function. Now I'm going to mirror the same process for the function unique left. So first off, before I give its signature and its description, what I want is to write a function called unique left, right? And it takes one parameter, LST, and then it's going to have some definition. So first off, what should unique left do? Describe what it does. Not literally, but what problem is it solving?
It deletes all duplicates of an element except for the first appearance of that element on the left.
Okay, sure. So I can write this as returns list, which has only the leftmost occurrences of the elements of LST. So what does that mean? What does that mean? Well, if I look at list 1, 2, 3, 4, 1, 5, 2, right? So does the number 1 occur in this list?
Yes, it occurs twice.
Yes, and where does it occur? Well, okay,
In the
it occurs
first-
here and here, right? So those are called occurrences of the number 1. So the number 1 occurs here and it occurs here. And the output list should have the same elements as list, but only their leftmost occurrences. So for example, if I look at the occurrences of 1, there are 2, and I'll remove all but the leftmost one. Now, if I look at the number 2, there are again 2 occurrences, and I'll remove all but the leftmost one. And then 3, there's only 1, 4, and 5. So for example, I can write at the bottom, check expect unique left of this list is that list. So that's a minimum test for correctness, right? And then I can give another test case. Here's another test case. It's important to note, as the problem statement said, that you can really have any type of elements. So you can have strings. moving the Zoom thing over. Actually, I can move it here. So what should the output be in this case? What's the list?
Everything
Someone who
except
hasn't
the
spoken yet.
last
Oh. Okay, fine. Go ahead.
thing except for the last high.
Yeah. Okay. Right. So, and what is its signature? What does it take?
It takes any list and it returns
Yes, a
any
list whose
list.
elements are of any type. So I can write list any. Any just means no restriction. And what does it return?
A list any.
Yeah. Now, how do I write this function? Well, how do you write this function? What's the first thing that you do? Someone who hasn't spoken yet.
You check if the list is empty, and if it's empty, you'll return the empty list.
So what are you doing there? No, that's, but what's thing are you doing that works for every problem? You're starting with what?
Right condition.
But you're starting with the template, what? The template for what?
Structurally recursive function.
Yes, a structurally recursive list function. So this is a function on lists, and we want to write it in a structurally recursive way. So you start with the template for a structurally recursive list function. Well, I already deleted it. And then a recursive call on rest list. So this is where we're starting. Okay, let's do the empty case first. How do I fill in the empty case? If I have an empty list, someone who hasn't spoken yet, what is the unique left of an empty list?
Empty list. No?
Yes. I'll also, instead of introducing a new list, I'll just have it output LST. If it's the same thing. Okay, now let's do what we did before. This is good. So, by the way, the problem statement had, I'm aware that you can't see it right now, several test cases. So the problem statement, I'm just copying this from the problem statement. The problem statement had this test case, for example. So actually a good way to start with check expect statement is that you should at least have the check expect statements that are in the problem statements. It's like a free test case. So well, let's say I add the number 5 onto this list. Then how does that change the output list? What's the output list now? Someone who hasn't spoken.
5, 4, 1, 2, 3.
Okay. So that's what happens there. Now, what if instead I added the number 1 onto this list instead of 5. Then what would happen?
List 1, 4, 2, 3.
So you add 1, but then 1 occurs in here.
So remove 1.
So you have to remove 1. Okay, now going from these cases, if you have unique left list, and then you consider unique left cons elements onto a list. What is that in terms of elements and unique left list? So, okay, someone who hasn't spoken yet. Actually, someone who has not yet submitted the homework. There are several people in here who have not yet submitted this problem for homework. I expect, can one of those people volunteer right now? Please? Okay, there are at least 2 or 3 people. Okay, I'm going to choose a person and call on them, unless someone volunteers. Okay, who has not yet submitted the homework? Say me. Oh, come on.
What was the question being asked?
Who has not yet submitted PG2? But I've already gone through with who has not submitted PG2. So identify yourselves.
Oh, I technically haven't, but I can't.
Do you have the solution though? Oh, you can't. Okay, never mind. That doesn't count. Anyone else? Arc, come on. Okay, your loss come exam time is going to be my reply. Right, going on to here. So how do I produce so okay. Okay, someone else volunteer? Just anyone.
Yeah.
Okay,
So,
sure, go ahead.
the
Wait,
idea
so
is
here's
that-
the, wait. Let me ask you questions. So there's a pedagogical lesson about how to think through this. What is unique left LST? So first off, what type of object is it?
It's a list.
Okay, it's a list of any, right? Okay, what is the meaning of that list?
Meaning of that list?
Yes.
It's a list with unique elements, with all the unique elements being the first unique element, first element of that type.
Of what?
What do you mean of what?
Of what? So, I mean, of all of, there are like a lot of lists that you can write down in Racket, right?
Mhm.
I want you to identify what list of all possible lists in Racket this is.
So list with unique elements. I don't think I understand the
The
question.
unique elements of what?
With the unique elements of the like the list it came from, of like the list that was
What list
entered,
did it come from?
a list of type any.
Wait,
Like
but
any,
what list is that? What's its name?
what's a what, sorry?
What's its name? What list?
I don't think I know.
Well, this is unique to the left of LST, right?
Yeah.
Okay, so in terms of LST, what is the meaning of unique left of LST?
The subset? A sublist?
Okay,
I
you
don't
you said the unique leftmost occurrences of what? Of the elements of LST is the answer that I was expecting. Right? So like
like
the starting list is a specific list, LST, right?
yeah.
So you can give the answer concretely. Okay, say the sentence now. Unique left is a list. Now, this list has a mathematical description in terms of LST. What is that mathematical description? Go.
It is the list of leftmost elements of LST.
Okay, sure. The list whose elements are the leftmost occurrences of LST. Good.
Yeah, leftmost elements. Yeah, okay.
Okay, now let's look at the list at the bottom. What is its mathematical meaning?
Is the list of leftmost elements of the consequence, of the consequence of
A con stands for constructor, but
yeah,
you just say the
constructor. Sorry,
cons.
yeah.
Cons.
Yeah,
You just say cons.
ELT, LST, and ELT there is always going to be to the left because that's how that operator works.
Right.
So
Okay. So here's the first thing that you observed. Let's pause for a second. You observed that no matter what, because unique left is a thing, when you look at the first elements of the list, if it's non-empty, will always be the first element of the output, right?
Yeah.
So you found this. Not first, cons elements, right? The first element of this list is ELT. We know that because that's.
Wait, why
what's
can't
been-
you use first?
I could write first in terms of this.
Yeah.
But okay, I already know what the first of this is going to be,
Oh,
right?
I guess yeah, that makes sense. That makes sense. Okay, fine.
And now what happens?
Well, then you just recursively apply unique left onto like LST.
So okay, you have this information. So you're saying that that's the answer?
Would that work? Oh.
So let's
Yeah.
look at this case in which you added 5. In the case that you added 5, that works, right? Correctly. But in the case that you added 1, you had to move one for remove this one, right?
Oh, I see. I see. Well, like I guess it would be like you'd have to take out whatever's like coming in from ELT. So it'd be unique left of LST somehow with ELT removed.
But you want to write it in a structurally recursive way. Okay, so you take unique left of LST and then what do? You said you want to remove element from it, right?
Yeah.
So let's just write that. Now, technically remove is a built-in function, but let's not make it a built-in function. Let's call it my remove. And this is basically like how we were doing proofs in week 1, or specifically how the proof of the first homework problem went, PF1. You were trying to prove something, and then you were trying to argue by induction. And then in the course of doing the inductive case, imagine sort of unique left of LST as being a logical statement that says, I know how to find unique left of LST. And then imagine this as being a logical statement that says, I know what unique left of cons element LST is. And then what you're trying to prove is that if you know this, you know this. And what's the proof? It is a procedure for how to get the second one from the first. Now, in the course of doing this proof, you realized, oh, but in order to do this, I would need to apply something called remove, to remove an element from a list. And that's like discovering that you need a lemma to finish the proof. So we realize then that we have something that we have yet to do. So first off, we complete the template definition. We can do this. So someone else, what's the template definition going to be now?
It will be cons the first of the list, and my remove that first element of the list and unique left of the list.
Okay, now our proof isn't complete yet. Our definition isn't complete yet because we still need to do my remove. But this is how we reasoned through the problem. We have some check expect statements. Okay, so that's for later. But then we also asked, what happens if I add an element to the front of the list? How does that change the answer from the previous list? And then once we were able to find this, and now how were we able to find this? We were able to find this because we knew what the meaning of this list is. That's why it's very important to have a mathematical description of the problem that you're going to solve. Because at the moment, you don't know what the literal solution is. You don't know how you write a function that does that. So don't think of it in terms of what the function does. Think of it in terms of what the function produces described mathematically. And then if you have this mathematical description written very clearly, then if you consider this, you know what its meaning is. It's the meaning of that list. It's a list, but it's not just any list. It is the list whose elements are the leftmost occurrences of any element in LST specifically. And then you have a similar mathematical description of this. And then the question is the inductive step in a proof by induction, or in this case, the inductive step in a definition of a function by structural recursion is knowing this, how do I get this? And then if I ask you, if you know this, how do you get this? The first question that you should ask in reply is, what is this? And it turns out that after you sufficiently clarify the meaning of this, the answer is usually not that hard to get. And so the most important thing is that you understand the statement of the problem. That's crucial.
Question.
Right? Yes.
I'm not sure about I don't understand what you mean by what you get from this. I don't understand the purpose of doing the thing about the answer. Like asking what kind of object that is. I don't really get that. Why? It's just
okay. So here, unique left of LST was defined as something specific, right? So
Yeah.
you've actually said that you do some things. That's a description of a procedure. Now, in the same way, some list you could describe what it does, but you could also describe it abstractly. What is the problem that some list is supposed to solve? The problem that some list is supposed to solve is that it should return the sum of the elements in LST, right?
Yeah.
Now, we also had a version of some list that used an accumulator. That thing solves the same problem, despite the fact that it has a different implementation. So what I mean to say is by what the meaning of this is that it's possible a problem statement is different from a solution to a problem. Similarly, apart from a function that does something is also a description of what the function does, as in what purpose the function serves, what it accomplishes, not literally what it does to get there. But if you just think of it as input-output, what is a description of the output in terms of the input?
I see. So it's like with proofs, where you have different ways of doing a proof. But
Yes.
Okay, I get it. Okay.
And not only is it like proofs, I've been pushing this analogy very strongly. This is the problem statement of the first thing that you're trying to prove. You have better know what you're trying to prove, right? If you don't know what you're trying to prove is, then you're definitely not going to prove it. You should at least know the statement, right? Okay.
Yeah.
Now, so once you very clearly identify the statements, so when you're just starting writing unique left, it's like, why is that important to identify what the statement is? Okay, we were about to see why it's that important. Yes?
So question is, why in the homework, when you state it needs to be done, you give the description, but not the signature?
So I don't give the signature.
No.
I expect you to write the signature yourself. The signature it's there. It says it takes a list and it returns a list, and then it says the list can have any type of elements in it.
Okay.
So I don't give the signature explicitly, but when you're writing the problem, the information of what the signature is contained in the problem statements, actually, in this case. If you look at the
so
problem
you're saying
statement
it's
carefully,
okay. So you're saying it's understood. It's part of the description of what needs to be done. You want to make it. We need to make it explicit in our program.
yes. Well, so remember
Or
the
in our-
comments don't
in our
actually affect the comments don't affect the behavior of the program, but when you're working through the problem, it's very good to write it down. In fact, that's how I'm teaching you how to solve the problem. So being able to write down the signature is an important part of understanding what it is that you're even trying to do. Okay, now here's where, so I was finishing this analogy about writing proofs. Here's where like the analogy goes. Using the template for structurally recursive list functions is basically like doing a proof by structural induction. You have the zero case, or in this case, the case of the empty list, and then you have the cons case. And the cons case is basically like an implication. Knowing this, how do I get this? And then in order to answer that, you need to have a very clear idea of what this is. And that is in terms of the mathematical description of this object. So if you understand mathematically that this list is the leftmost occurrences of LST, then if you cons on an element, you can see how that changes. And you should go through some specific examples as well. So always start with some examples. Start with, if the problem has a sample inputs, definitely use that sample input. And then see how that's what changes if you modify the list by consing on elements at the front. And then see if you can, yep. Sorry, you said question?
Yes. Oh, I just forgot it. It'll up to me, but oh yes. Okay. So you've also made a statement that while we are writing this to destroy or change any elements or any lists, here you are stating you are going to remove something from the list. So you are going, so if you get if the first element is considered is already in the list, then you want to remove it from list and then keep or add that you just discovered, the new one, because you want to keep the leftmost occurrence. So why are you saying remove?
Okay, so to answer that question, well, we knew that elements had to be the front elements of the list. And we knew that we had to use this information somehow, right?
Mhm.
So how do I put them together? Well, I somehow put them together. I remove elements. Now here's the key point. What does that mean? Indeed, what does that mean? That's not a, this isn't a play on things. This is the most literal and most important question. What does that mean, right? So let's determine what that means. Let's write my remove. So now you've discovered that you need to prove a lemma. Let's see what the statement of that lemma is, right? So first off, let's say it's going to use ELT and LST. Okay, what is the signature of my remove? Sorry, was your question about what my remove does, or
Well, I guess ultimately, but it was also more somehow you built a list, or can I not say that?
okay, so you're not changing the list.
temporary-
You're building
you
a
have
new
like a-
list.
Right, you're building a new list, but the list you're building, it seems like it's temporary, a temporary list, because there is an element that you're going to be looking at now. And
Well, the way that you should think about it is that
Yeah.
unique left list constructs a list. So that produces a list, unique left list, right? And now in order to get the answer, I need, that list is inadequate. So for example, if that list is this list, then I need a list with one removed from it. I don't think of that as a verb, like I'm actually changing the list. I'm constructing a new list. The meaning of that list is that it is the same list, except it doesn't have elements. We've removed all occurrences of elements. So don't think of this as a verb that does something to it. Think of this as the list obtained from this list by removing elements. But you haven't actually removed elements. You've just constructed a new list satisfying that property.
okay,
Okay, so now you've discovered that you have to prove a lemma. This is where the describing the problem that you're solving is incredibly important, because now you're one step removed from the original problem. And now you need to understand, this is like you've discovered a new goal. You need to now understand what the new goal that you're solving is. If you don't explicitly state what my remove does, then it's like you're starting this problem without knowing what the problem statement is. So first off, what is the signature of my remove?
It takes a number as well as a list of.
Well, it doesn't take a number. It's any.
Okay, it's n. It should
And
be n.
any with what?
With a list of n.
And what does it return?
It returns a list of any with all the occurrences of the previous any removed.
Okay, so okay, what's the description then? The description is that returns what?
A list of any.
Well, no, that's what the type is. Now, what's the mathematical description? You're allowed to use LST and
Okay.
ELT in this description.
Returns a list which has all of the occurrences of the input, the
LST.
I see, that has all occurrences of the elements of
With all, okay, so finish the sentence.
has, but with are we gonna call that element ELT?
Yes.
Okay, with all occurrences of E.
Yes. So that's a description. So that this is a mathematical description of what the output is. So for example, you should write tests for every single function that you solve. So you can write, for example, check expect my remove. Let's say we're removing 1 from this list. That was a thing that we needed. Then the answer should be that. So that's a test that came up when we were working with the previous one. So you should write a test for the new function that you're writing, right? That's an important thing. Okay, so when you have elements is going to be called is a non-accumulator parameter, and the template for structural recursive list functions with a non-template parameter looks like this. Now, what happens? Okay, the template looks like this. I don't need to.
Question.
Yep.
When you say non-accumulator, that means like a primitive element, like element or boolean or what?
So let me explain this.
Empty.
Let me explain it right now. So what a non-accumulator parameter means, so if you have a function and its definition involves the function calling itself, that's called a recursive call. So in the template for list recursion, there is going to be a recursive call. If you look at ELT, that parameter goes along for the ride. If you had an accumulator parameter, it would somehow get changed in the recursive call, right? So for example, in some list written as an accumulator, you'd add something to it.
So it
But
can be
here-
anything as long as
You're
it's
not changing
just
it.
informative.
Yes. It's very important that ELT does not change. If ELT changes, then you're not writing a structurally recursive function. And on the exam, you will have to write structurally recursive functions. So basically, I need to tell you what the answer is in terms of this. The only thing that changes is that I've stripped an element from LST. And now the new answer should be determined in terms of these two things. So that's the template, right? Now let's write some cases. So if I remove all of the ones, then I remove these two, right? Now let's see two other cases. Let's say I add 1 to the front of this list, or I add 2 to the front of this list. Okay, what happens in this case? Well, does the answer change?
No.
What about the second case? Does the answer change?
Yes.
Yes, so it changes like this. But how can I describe that in terms of this list? If I don't want to write this, if I want to write something in terms of this list, what do I write?
Cons.
Yes.
Yeah, that listed too.
So sometimes it returns the original list. Sometimes it returns cons to, cons the first element of the list, right? When does one case happen and the other not? Or more particularly, if I consider my remove element from list, and now instead I consider my remove elements, I guess cons E2, let's say E2 LST. Actually, let's call it FST. Then what's the answer?
Well, I need to establish whether or not FST equals ELT.
Okay, so we can say if equal. And here's a very important thing. If you have like the equal sign, that works for numbers, but it doesn't work for any other type.
Oh, okay.
So if it's any, you have to use equal and not the equal sign because that only works for numbers. Okay, so what are we comparing? What are we comparing to what?
ELT and FST.
Okay, what if they're equal?
If they are equal, then you just output the same list of myRemove, ELT, LSC.
Oh, right. Recursive call. And otherwise?
Then it's cons ELT to myRemove, ELT, LSC.
No, cons FST.
Yeah, cons FST.
Okay, sure. And if we look at the statement, this is an if statement. So if you look at the two branches of the if, only one of these will get evaluated. If evaluates the condition, and then it evaluates one of these. So it won't make two recursive calls. So we have this, right? Okay, so how do I fill in the template?
Well, we can identify where we call cursive calls. I guess for if we can say do the same thing, if equal ELT of first of list, and then it's myRemove ELT.
Yep.
LSC.
And otherwise?
Then it's cons first list to myRemove ELT rest list.
Yep. So now I'm closing the if. Then I close that, then I close that, then I close that. Now that's a bit ugly, so I'll just space it out like this. Now, just so my code's not going to run because I have this, I can actually do this to comment off a bunch of lines. So that's located somewhere in the menu. There isn't a shortcut for it, which is a bit unfortunate. Okay, so what we've developed is the function myRemove. Oh, we haven't finished it yet. What's the empty case?
The empty list?
Yes, I'll prefer to write it as LST.
Okay.
It's empty, it's the same thing, right?
Yeah.
Okay, so here I've developed that function. Okay, here I've developed this function. So I've now completed the proof of the lemma, and the proof of the lemma should let me prove the main theorem. Now let's see if all of my check expect statements pass, right?
Question.
Yes.
The tests only test particular cases though. How do you know it holds like all the time? Like how is
You
it like
can
a proof?
prove it, but the thing is that you should not submit to Marmoset without doing this is the bare minimum.
Okay, but like how do you prove it?
Oh, well, I'm going to assign a problem this week about proving theorems about lists.
Okay.
Now, here's the thing. Sometimes it's hard to that our theorem proving language makes it very hard to describe something like this, right? So the theorems are actually going to be that one function does the same thing as another function. But later at the end of the class, when we do formal logic, we'll actually see a logic that's expressive enough to give statements like this. Okay, so, okay, what was the boon from this entire discussion? It was how to write functions. On the exam, you will be asked to write, okay, I am not going to send you this file. I'm going to send you the file that I'm going to develop after this. Your max homework score, if you haven't submitted this problem, is now capped. But more critically, you should now see sort of the analogy between proving things and writing function definitions, and you should also have this recipe. Now here's, by the way, so the problem about permutations, how do you solve the problem with permutations? You write down what you're trying to solve. You write down the template for structurally recursive list functions. You ask, what is the meaning of going from one case to the other? You identify what you would need to solve it. You realize that you need to do a lemma. You take your lemma. It'll be of this form. You clearly identify the problem that you're trying to solve. You write the template for structurally recursive list functions with a single parameter. You write these things down again. You see, how do I go from one to the other? Then you write it down. And in order to figure that out, you need to know what the meaning of the problem is. So you need to very clearly state the lemma that you're trying to solve. And you'll discover, I need another lemma. And then you'll do it again. So there are I need 3 helper functions. So my solution has 4 functions in total. And if you follow this recipe over and over again, it'll just keep, so perms is a hard problem because you have to do this process of figuring out how to solve the thing 4 times over. And like a game of broken telephone, if you don't clearly identify the problem that you're going to solve, it's going to be completely impossible to get to the 4th iteration, right? If every single time this happens, you lose a bit of information and clarity about the problem that you're trying to solve. If you don't state a clear statement, then the entropy will overtake it by the 4th time. You'll have no idea what's going on at the end. But if you clearly state it, then it'll be as though each time you're starting fresh. You have a new goal. You can forget about everything that occurred outside of it. The only thing in the universe that matters now is writing the function myRemove, right? You can forget about the fact that we started with unique left. Any questions?
Yeah, a quick one.
Yes.
Actually, 2 questions. The first one is, if we go back to the unique left definition, does the order in which myRemove and unique left are applied matter?
Absolutely. If you change the order, then you would get less than 50% on this question on the exam, because it would not be structurally recursive.
So if I do unique left, I see.
It would work, but it would not be structurally recursive.
Because the unique left has to be applied to the rest of the list.
Yes.
Okay, I see. Thank you. Another question that I have is, on the exam, are we required to write those 3 lines every time before we write the definition?
You should.
Okay.
I don't think I'll deduct points if you don't, but you really should. But you will most certainly have to write the functions in a structurally recursive way. And you will also have almost no built-in library functions that you're allowed to use. Notice how this function right here, what did I use to solve this function? I used the ability to define functions, empty, cond, first, and rest. That's all I used. And if you looked at the notes, I'm going to update the notes and add a lot more information. But at the 3rd section, I describe what each of these functions does. So in order to solve this problem, all that you need to know is what the meaning of function definition is, cond statements, empty statements, Okay, I guess I used an if. I could have written a cond instead of an if. Okay, but their if and cond are a bit similar. Equality, first and rest, and the idea of how it is that you solve structurally recursive problems on lists using the template for structurally recursive list functions. So with only those ingredients, you don't have to understand any complicated programming languages concepts. You don't have to think about memory. You don't have to think about execution. You just need to understand that small set of concepts and put them together in the right way. And here, in this first hour of class, I've walked you through how to do that. And that's what you are supposed to learn by doing this homework. And perms is a very good problem because it's a problem where you have to do this 4 times repeatedly. And there it's really important that every new statement, every new lemma that you discover that you have to prove, you don't let the information of what the problem is that you're trying to solve degrade. Always keep in clear sights, know exactly what you're solving, because that tells you what the meaning of these things is. And if you understand their meaning mathematically, then you'd know how to go from one to the other. You need to know the statement of the theorem that you're trying to prove in order to prove it. Okay, so that took very long. Are there any other questions? I'm going to run a break now and then we'll continue. And I still expect perfectly correct solutions for everyone for both of these problems ASAP, because I'm assigning you homework this week. Was this helpful?
Yes.
Yes.
Okay. Let's run a break until, let's run a short one until 2:56. Okay. Has anyone thought of any questions? Okay, let's restart. And I want to make one thing very clear. The point of the exam is to get everyone caught up on the material and ensure that they understand it. If you are having any difficulties with the material, you should reach out to me. If you do not reach out and you just let things slide until exam time, and you don't follow up on completing the work, then you deserve the grade that you get. If you should really, really reach out for help. That is it's part of your obligation. Like, you're doing everything right if you reach out for help and we work through this. But it's necessary that you take that step. And also, the other most important point is the exam is going to have problems that are not direct modifications of the homework problems, and it'll have about as much problems on it as 75% of all of the assignments that we will have done in 3 weeks. And it'll be done in much less time than that. But how is it possible to do this exam then? If you learnt this problem-solving strategy that I just walked through, so if you understood what I did here and how I went through this problem, how I explicitly stated what the problem statement was, and what it means to use the template for structurally recursive list functions, then how I went through these examples, and how that got me to find what the general relationship between these two objects is, something which required knowing the meaning of these objects, which required having a clear statement of the problem that I was going to solve. That thinking process is the main point of this assignment. Like, implementing unique left is completely unimportant. The details there are, that's not the point. I will never ask you to implement unique left again. The point is this process, what I outlined through here. And to summarize, the process is, so first off, start with the header of the function. Give the function some parameters, give it a name, describe its types, and then describe a sentence that says what it does in terms of the parameter names. Okay, but that's also very specific. So the header is just a tool for figuring out how to write the right definition of a function. But your function has to be structurally recursive, and you always start with a template for structural recursion. And then you think through it. And you also write some tests using check expect statements. And if the problem statement has sample input and sample output, then you better check those. By the way, checking is harder for the permutations question because the order in which you output the list doesn't matter. So that's going to make one, so it's hard to write a check expect statement for perms. And then you go through some examples, you figure out what the pattern is, you form this, but while forming this, you may discover that you need to prove something else or write another function. And then you forget, you can complete the template, just so that's there, and then you can forget everything that you were doing before. Now, the only thing that matters in the universe is completing this function, and you do the exact same thing from the start up over again, as many times as needed until you crack the problem. And this really is a bit similar to how we did proofs, right? Do people see that?
Yes.
Yes.
Okay, so let's move on to new material. Okay, I'm going to start it like this. Suppose I want to write a function called contains cats. And this function is going to take a list of strings. So strings are enclosed in double quotes. And it outputs a Boolean. And what it does is returns true or returns if and only if, let's say, okay, the list contains the string cats. And when I say the list, I really mean LST, which is the first parameter of this. Okay, how do I write this function?
The template or
Good.
all
Yes,
of the
that's the
depth?
first thing.
Okay.
So by the way, for the sake of time, I'm not going to go through all of the steps. And some, maybe you can see what the definition is already. So what should the zero case be? Or rather the empty case. If the list is empty, does it contain cat?
False.
False.
Yes. Okay, let's suppose that the list has a first element. Then what do we do?
Check if the
We compare the first element with cat.
So if it's equal, then what happens?
True.
And return true.
Yes. Otherwise?
See if it contains. See if the rest of the list contains cat.
And so
That
that's
is-
this. So first off, if we look at this expression right here, right? Let's actually go out of step for a second. If I look at this, once it's evaluated, what type of value is this?
Boolean.
Okay, what is the meaning of that Boolean?
True if it has cat and false if it doesn't have cat.
If what contains cat?
List.
Not list. If
rest
what
of-
contains cat?
The rest of the list.
Okay, that was quiet, but you said restless, right?
Yes, microphone.
Okay. So this thing right here is a Boolean. And of all Booleans, of which there are only two, but of all Booleans, it is a Boolean that satisfies the mathematical description of it is the Boolean that represents whether the rest of the list contains cat or not, right? And then, well, if the first element of the list is not cat, then whether the list contains cats is really that Boolean, right? Does everyone see that?
Yes.
So that completes the definition of contains cat. And we can test it. Let's test it with a check expect statement. So here it should return true. And here it should return false. Okay, so we have succeeded in writing a function contains cat. I mean, as was pointed out, we haven't proven that it's correct, but it looks pretty compelling that this is right. Now, suppose that I want to write a function contains dog. Well, if you want to write this function, really you're just copy and pasting your code, right? Yep. And it's bad to copy and paste code. So that suggests that, like, if you really want a contains cat function and you might ever use it again, it's probably better to, instead of writing that, write the function contains. Which takes, well, let's actually just consider the function for strings right now. So the first parameter is a string. Let's call it my contains. And then well, what's the statements? Contains true if and only if list contains str. And what is the definition of the function? I should probably rename this. So if I were going to modify those two functions to be my contains, how would I change this case?
Just swap out the dog string with the string.
Oh, thanks for pointing out a mistake. I call this str and the. Right? And then what do I do here?
Change from contains cat to just contains, and then add in the string parameter.
Yep. And this is a non-accumulator parameter that just goes along in the ride with the structural recursion. So what happened here was that I had a function contains cat that did this very particular thing, and a function that contains dog. And then if I looked at all of the functions that were similar, really all of them are generic instances of this my contains function, where this non-template parameter is really something that just goes along for the ride and parameterizes which one of these functions I have. So another way that I could define then contains dog, let's call this contains dog to list, is that it just outputs the result of my contains with the string being dog. And I mean, you'll still have this, but it's just going along for the ride, and it substitutes str here for dog. So this is an example of abstraction. Well, generalization. I've abstracted away dog and cats. To non-accumulator. That, and this is sort of my slogan, goes along for the ride. That's the slogan. Okay, now let's say I have, this is the good case. Let's say I have a list of numbers. And I want a function that also returns a list of numbers. And I'll call my function squirrel. And what this function will do is, I'll give names to the parameters. And so it will return a list, LST, but with each element squared. So let's write this function. How do you write it? Someone who hasn't spoken yet. Oh, Amanda, are you there? Okay, no. Anyone who hasn't spoken yet? Okay, someone, go ahead. How do I write squirrel?
Are we going to use our template?
Yes. Okay, what do I do now? Well, okay, if it's empty, what happens?
You return the empty list.
Yes. And otherwise? So first off, what is the meaning? What is the meaning of square all rest list?
It's a list containing all of the rest of the elements squared.
Yes. Okay, and so what is the meaning of square all list?
A list containing all of the elements of the list squared.
Okay, and how do I go from one to the other?
You cons the square of the first list, or yeah, the first list times itself onto
Yep.
square all the rest of the list.
Although, yeah, so that works. So that completes the answer. But, I'm actually going to do another thing. I'm going to write a separate function square.
Question.
Yep.
Does Racket have map?
Shush. Quiet. Don't. I mean, you saw what I just did above, right? Don't. No. Okay, square's the number. Okay, so let's define this function square x, and it returns x multiplied with itself. So then instead of doing this, I can just write square. First list, right? And so that definition works, right? Let's write a test. And what should the output be? What's the second number?
14916.
Good. Does it pass the test? Yes, it does. Okay, now let's suppose that I want to write a function. Let's suppose that I have a function. Well, okay, I have a function add1, right? Add1 is a function that exists. Add1 all. So it takes a list of numbers and returns the list, but with each element, being having one added to it. And remember that in Racket I have a function add1, right? So how do I change this definition?
Just like, instead of like the square, you think you just do add, oh, plus, not add.
Oh,
Yeah.
well, we have add1.
Oh yeah, then just that.
Okay, so as with this example, it really looks like you might want to generalize away this function, abstract it into a separate parameter. And what does that do? Well, it applies the function to every element of the list. That's called map. So if I just abstract it, okay, let's leave the signature. Well, the first thing that it takes is a function. Actually, let's not write. Let's leave the signature just right now for here. Now to give it names. Let's say it takes a function and it takes a list. And what it does is, well, it returns LST, but having applied F to each element. And I'm just going to copy and paste this definition. What do I modify?
I'm not sure because you have two functions there, the add1 and the square all.
Right, but there is no add1 and square all. There's now just F. So if I looked at the definitions that I had above, here I'm going to do this. Change to this layout. This layout looks awesome right now, but remember that in the recording, there's going to be a huge video box at the top. So that's one disadvantage of this layout. Command-Shift-L to switch to vertical layout. Okay, so in square and, sorry, this function is not square one, it's add1 all. So if we looked at contains dog and contains cats, then we had cat here, we had dog here, and then contains dog and contains cat. And how did we abstract it? Well, we abstracted away dog and cats to the string str. And okay, so we changed the function name, and then this abstracted parameter went along for the ride, right? Does that make sense to everyone?
Sure.
So here, I have square. Here I have add one, square all, add one all. And now I want to abstract it away into a function f. What do I do? You know what? Actually, that's a bad name. It shouldn't be called my map. It should be called f all. Which could be interpreted as, okay, what the function f all does is it's done with this shit and it's going to not do anything. Well, that's another way to interpret the meaning of the function. But no, f all. Or maybe func all. Okay, what does func all do?
It applies f to all the elements of the list
Yes.
of LST. So
Now, how
we
do I
would
modify it?
switch. We will switch add one to func. No, to f. Yeah. Then switch square all with func all.
And what else?
Func all f rest of the list.
Yes. Now, okay, so my language right now isn't set to, where is it set to? It's not set to beginning student. I'm going to switch the language to beginning student. Let me just save this guy as EG4 and let me save this guy as EG5. So I want to change, I'm actually going to change the language to back to what we were doing before, beginning student with list abbreviations. And the function says no. Expected a function after the open parenthesis, but found a variable. So it doesn't like that. But that's only because we're doing beginning students where functions can't be parameters. So that seems annoying. It looks like this is a thing that we'd like to abstract. So what we do is we add more features to the language. So instead of doing beginning students with list abbreviations, we're going to move to intermediate student with lambda. And now I'm going to rerun this. And it's going to be fine with this definition. And so, for example, I can say func all, add one, list 1, 2, 3, list 2, 3, 4. So I passed add one as arguments. I can also say square. And, well, what happens if I just type in the function add one into here? It returns add one. It returns square. So what we actually discover, remember, that Racket evaluates expressions. That tells us that add one is a value and that square is a value.
So lambda makes functions count as data types?
That's next. Yes. I'm going to explain how the function definition is actually not inherent part of the language. That all you need is definitions of names.
Interesting.
Okay, let's, so functions are values. That's one lesson that we learned. Experimentally, if I type in a function name into the REPL, so this language is called intermediate student language with lambdas, so ISL plus. I get that it prints that function name back. Well, it prints the function back, but it instead of how does it print the function? It prints its name. But like it prints its name. That's how it prints, because that's how print works. ISL plus. But really it returns the function. But then that function gets printed as a name. So functions are values. No, but like, okay, this says this sentence is wrong. I need to correct it. Okay, so the way that I correct this sentence is I put on all caps. Okay, that's right now. Yes, that is, I think, a correct statement. Yes, functions are actually values. This is, functions are values. No, but really, functions are values. Okay, any questions about what we did there?
When you say functional values, do you mean the evaluate functions or functions in the Lambda language?
What I mean is that when I type in something into the REPL, it evaluates that expression.
Oh, okay.
And we found that when we type in functions in here, well, it prints what the function is, but the way that it prints the function is its name. But a function is already a value.
Okay, so they're values in the intermediate with Lambda.
Yes.
But they're not values in the beginning student?
Yes, because functions on their own do not make sense in the grammar of beginning students.
Okay.
If you define a function name and then you try and evaluate it, it'll throw an error because it will read a function name. Like, so what the error that, let's say I switch languages again. So let's say I'm going to just put this as, let's say a test expect. Check expect. That this should return, let's make it square. That's a bit more interesting. 149. Okay, so here it's happy with this test, all tests passed. Now, if I switch to beginning students with list abbreviations, and I try and run this. So first off, it's going to say, well, f isn't a parameter, but let's say add one. Sorry, f is not a function, it's a variable. But no, variables can be functions, but in beginning student, they can. Let's say I just type in add one. It'll say expected a function call, but there is no open parenthesis before this function. So beginning students will say, oh, but that's a function name. But if you're using a function name, it should be a function call. And so there's no grammar rule for what happens if you have a name that's a function name. Because in beginning students, the grammar says that if you have a function surrounded by parentheses and the things here are values, then it'll evaluate this by substituting. So that tells you how an expression like add one 3 is evaluated. If add one has a definition in code, if it's not a primitive that's sort of built in directly in assembly, then it'll substitute 3 into the body of add one. So that makes sense. But there's no rule for this. And it's not explicitly declared as a value. So since it's an expression that's can't be reduced and isn't a value, you're in a stuck state and the program throws an error. But that doesn't matter, because if we switch over to a language that has what are called first-class functions, functions are values. Functions are pieces of data. They can be passed as parameters. As parameters. And not only that, but they can also be returned from functions. much in the same way as numbers can. Any questions? Okay. Let's do this first. So I'm now going to introduce lambdas. Lambdas are functions without names. And so, for example, if I consider the square function, I had this function square, right? Let's say I want to take the name square and I don't want to, here I'm defining something. I'm defining what square of x is, right? I mean, the word define appears there. Suppose that I don't want to define anything. Define introduces new rules into the language. I don't want new rules. I just want the computational abstraction of squaring something. So I can write it like this. Function definition introduces new rules into the language. Actually, any definition, all definitions introduce new rules into the language. Why can't I just square abstract the process of squaring a number in peace? I.e. without introducing new language rules. And you can. So let's say cute. You can. With lambdas. And so the way that that works is you can type in, okay, so first you can write the word lambda. And then you write the parameters of a function, x. And then you just say times xx. So this here, let's say I run this program. So this thing right here, it's a value. Now, the way that it prints this is in this form, which is a bit unfortunate. It's a bit of a, like, it abbreviates some details. But this is a value, basically. It is a value. No, it's not basically a value. It is a value. The printer just prints it like this. But this defines a function without a name. But what can I do with a function without a name? So how do you think I use this function to square a number? Okay, how would I use square to square a number? Let's say I have the function square. How do I square a number using square? How do I square 2? I didn't hear. Say?
Times 2.
No, but using the word function square.
Okay. Square 2.
Yes. Now this lambda is supposed to be an abstraction of that process. So how do I use this lambda, which is a function that does not have a name? It does not have a name. How do I use this nameless function to square a number?
lambda 2.
Well, you mean that expression, this entire expression, right? Lambda isn't a name.
I see.
So
So
do
it's lambda 2 then times 2 2.
You just input,
Well, go ahead.
do you just input 2?
Do you mean after this, like this?
Yeah.
Yes, that's how it works. I think the suggestion before was something like putting a 2 here. Let's see what happens when you try that. It'll say lambda was expecting a variable, but found a number. This is similar to, for example, if you try to define square 2. In a very ironic way, square 2 not only means is that it's a second version of a square function, but specifically with 2, and puts 2 for the parameter. What would happen if I ran this? It would complain saying that the function definition expected a variable for its parameter name, right? But you can't, so 2 isn't a variable, 2 is a number. So that doesn't work. And similarly, you can't put something for lambda. Instead, you use lambda instead of the function name. It doesn't have a name, so you just put the lambda. So when I said that Racket was based on a language of S expressions, there are that's a lie in several ways. And that it's not a lie. It's a lie on this. At first, it appears to be true on the surface. Then it appears to be a lie on the surface. And then if you go very deeper, it's not actually a lie. But right now, it looks like it's a lie on the surface because the node value of this expression is actually a lambda. It's a complicated expression. So that doesn't look like a node label. The way that this is actually fixed is that the actual AST for this is apply as its node, and then this is the child's, and that's the second child's. But don't worry about that for now. So this is another way in which you're breaking the language of S expressions. But we can write anonymous functions using lambdas. And I can call this with, I don't need to comment these off expressions.
So what's the practical use of the lambda? Is it to define a function, an anonymous function, just on the fly because you're going to use it?
Yes, that's a very good use of it. So for example, if you wanted to write square, but you didn't want to write a separate definition for square, you could just say funcall lambda. Oh, okay. Here's the other thing. Instead of writing the word lambda, you can press. So on OS X, it's command. Okay, let's say command backslash. This is on OS X. And then on Windows, you do control and backslash. And what that gives is a lambda. So instead of writing the word lambda, you can just put the symbol lambda. And then instead of defining square, you could just say funcall lambda x times xx onto list 1, 2, 3, 4. I've abstracted squaring into a lambda function, and the list I now funcall this function. It doesn't have a name. I didn't have to give it a name. I didn't have to give it a language definition. I just put it in, and I applied it to the list, to each element of the list. So this is where functional programming really gets its name. It gets its name. Any questions?
Question. So is this related to what we talked about before, the recursion? Or there's no relationship? This is something
Oh,
brand new, totally different.
I can actually explain that to you. That's one of the topics that I'll explain. Yes, I can explain to you what the relationship between recursion and higher order functions is. That's a good point. Let me do one example first. Suppose you have, let's say, here's the function that I can abstract. So let's say I want elements greater than 0. Let's call this function thresholds. And what threshold is going to take is it's going to take a number and a list of numbers, and it's going to return a list of numbers. And let's say thresholds big. The function, the parameters of threshold big are the number, let's say x, and the list. But maybe let's call the number no. And what it returns is returns list with only those, returns a list with only those elements of LST that are greater than none, right? Okay, how do I write this function?
Cond first to establish the recursion template.
Your mic is very quiet.
Yeah, I don't really know what's going on.
Okay. Yeah, okay, now I hear you. Okay, let's do the template. So num is just a parameter that goes along for the ride. Right? Okay, what happens if it's empty? Tell me.
Then we get empty or just list.
Yep. And now, what is the meaning of this?
So we need to establish if first list is greater than num. And
Oh, but
if it
before
is-
that,
Oh.
answer the question. What is the
Okay.
meaning of this expression?
Oh, that's just when you apply the threshold check onto the rest of the list after you're taking care of the first of the list.
So what type of thing is it?
It's it's a list
Of what?
of numbers that are
Okay, and what of all lists of numbers, how can you describe that list of numbers?
they're all going to be greater than some value num.
Oh, that's true, but that doesn't specify exactly what list it is.
It's gonna
Like-
return a list of numbers that were in the original list that
What
are
is the
greater
original
than
list?
num. LST.
No. I mean this expression, this second one.
Rest list.
Yes. So it's going to return what? Say it.
Gonna
Full sentence.
return all the numbers in rest list that are greater than num.
Okay, yes. A list of those things. Yes. Good. Okay. Then similarly, you can ask what the meaning of this is. Okay, how do I go from one to the other?
Well, you're going past the first list if it's greater.
So you're saying I should
Num.
check if first list what's relative to num.
Is it greater?
Okay, greater than first list num. Okay, if it is, then what?
We want to add it. So constant to the rest of the list.
And otherwise? Otherwise what?
Well, you don't really want to do anything. You don't want to add it.
So what do I return?
The rest of the list.
No.
Wait,
The threshold of the threshold. The,
Yes.
yeah, rest.
There we are.
wait, shouldn't cons have two arguments?
Ah,
It
thank
should
you.
have the first
What are
list.
we consing on?
We're counting on the first list is greater, and that's
Good.
in the true position. So
Nice catch. So if it's bigger, then it satisfies the condition and we cons it on. Otherwise, it's just threshold big rest list. So let's just. So though these blue things are the evaluations of these expressions above, I'll just leave them sitting there. And then I can try like threshold big. Let's say 2, and then I'll take list 2, 3, 1, 5, and 2 and 1 will get removed, right? Okay, but there's a natural way to generalize this. Specifically, you really were doing a test. You were doing this test right here, greater than first list num, right? So you let's call this function my map. Sorry, my filter. It's going to take. Oh, by the way, okay. I forgot one thing. Sorry, completely going out of. Here we had a contract and we had question mark for the contract. Functions are values, which means that functions have a type. So what is the type of a function? Well, we'll say that the type of a function is its contract for the moment. So in this case, what is the contract of funcall?
List and gives you a list.
So the second argument is a list of
Oh, and a
something,
function.
right?
A list and function gives you a list.
Okay. What is the type? What is the type of the function, and what is the type of the elements in the list?
Well, I guess the elements of the list have to be like, the same type as the thing the function takes, right?
Oh, okay. Let's just look at an example. Let's just say for the moment, we were doing an abstraction with numbers, right? Let's just say we restrict it to numbers at the moment. So let's say this is a list of numbers. What should the type of the function be then?
Oh, takes numbers and outputs, actually outputs anything. Doesn't have to output
Yeah.
numbers.
So we can write that. Yeah, so that's a valid contract. It doesn't necessarily have to output numbers, right? Okay, so sorry, we were doing, okay, does anyone have any questions about that? There are some questions that you should have.
Does it have to be applied on a list of number? Can't it just be?
Yes, that's a good question. That's the question that you're supposed to ask, right? I mean, why can't the signature be? So here we discovered this very big functions or values, right? So we were very excited about this. So we got distracted for a while. So let's forget about threshold big for a second. And let's say, wait a minute. Is the contract of this guy really this? Really this? For example, why not? Well, why not, for example, saying that it's restricts to number, like the thing we were considering before? Or why are there numbers anyway? Why not string to any list of strings?
That's
Right?
okay too, right?
Yes. So, but all of these are three different contracts. So there is, this is where we have our final level of abstraction. So first, we took has cats, contains cats, and contains dog, and abstracted away a string. Then we took, let's say, what were these functions? These were add one all and square one all. Square all. And abstracted a function. finally, we can look at, well, for example, we can talk about lists of numbers. And we can talk about lists of strings, right? And what do we now abstract away?
The data type?
Yes. So, and then we abstract away the data type. And then we just write list A. Here, A is a meta variable for a data type. Then, if we look at the contract of here, by the way, any is a data type. So let's just write a comment. Number, string, and any are concrete data types. So any is as much of a data type as number is, right? The letter A is not a data type on its own. Here, we're using it as a meta variable for a data type. So for example, A could be number or any, but it's abstract. So if we looked at this function, right, we could have abstracted two things. Here we had any and here we had any, right? And we replaced any with number. And here we took number, and replaced them with string. So the actual contracts, most general, of a func call is what? Does anyone want to take a guess?
You need a variable, right? To like put into both places.
Okay, so what do I write?
Well, let's call it F type. Then if you have like F type maps to
Well, okay,
all.
it's not just any F type. It's going to take one argument and return one argument, right? It's important that it only takes one argument.
Oh, that's correct. Okay, yeah, that makes sense.
So what is the type of that argument?
It'll be A to A.
Okay, so you're saying this. Let's go with that for the moment. A to A. Then what list does it take?
A list of A
And it returns?
to a list of A.
Okay, but notice, look at this example here. If we take A and we substitute number, it's impossible to get this contract from that. If you substitute, all of these have to be the same, but here they're not all the same, right?
So make them all different meta variables.
So what do I put here?
Any.
A to B.
B. And then what's the input?
List C to list D.
List C?
Um,
Okay, what happens if I apply
no,
a
list
function?
A. I'm sorry.
Yes.
Wait. Depends what we're looking at.
Yeah.
To any was B.
List B. Yeah. So, okay. These are called type variables. What this means is that if you give a func call parameters of types A to B. I'm going to put parentheses. And list A, let's say of types, write this. Then you get an output of type list B. So here, let's do another example.
Question.
Let's see if this name is already defined. No, it's not. Okay, ID is going to be a function that returns its argument. Let's say, here's the definition. Okay, what is its signature?
Any to any, right?
That's one signature. That is one signature, but if you give it a number, then it returns a number, right? And if I give it a number, then I'd like to know that it returns something of the same type. That's useful information. Knowing that it returns any is completely useless. To say that it returns any just says that it returns at a value of any type. But I'd like
Okay,
more
so-
information.
A to A then. Okay.
Yes. So the type really is A to A, which means that if you give it something of type number, for example, it'll return a number. So for example, since 5 is a number, ID 5 is also a number. But I can say something else. Also, 5 is any. Since 5 is any, right? 5 is any. That's any match is a type that matches any value. ID 5 is also any. But this signature right here, it gives useful information. So we'll see this in the last week of the course. We'll have, in fact, this is where for all statements will come in. We'll write types like these as for all A to A, but that doesn't, that's for later. Okay, so there are 3 types of abstractions that we did. First, we abstracted away just a data parameter. Then we abstracted away a function, an actual computational process. So here we abstracted away some value used in a computational process. Here we abstracted away an entire computational process itself. And here we abstracted away a theoretical statement that can be made about the computational processes. So this is some next level meta trippy shit. This is good. This is very nice and abstract, but this should be interesting, right?
Can we go even further?
We will at the end of the class in one way. We will have return types that depend on the value of the arguments. So it'll take, let's say, a number, and the type of the output will depend on what number it's passed. That's called a dependent type, and we'll see that at the end of the course. Okay, so yes, but okay, those were 3 steps of abstraction. Okay, getting back to where we were going before. And by the way, I should say one more thing. Funcall is actually called map. So for example, I can say map square onto list 1, 2, 3, 4, and it's a built-in function. Okay, there are a lot of values, but this is the last one. So that defines the map function. Map takes a function and a list, and it applies the function to every element of the list. And its contract, the contract of map is this. It takes a function that goes from A to B. It takes a list of A, and it returns a list of B. Okay, now we went to threshold big, this function right here. Now we'd like to abstract it away. So what would we like to abstract away? What is the idea that goes on behind threshold big? And we're going to abstract it in several ways. We're going to abstract it, and then we're also going to abstract its signature. So what was the idea going on here? What role does threshold big really accomplish?
So there's
It-
some function. Oh, sorry.
Go ahead.
Okay, continue. First person that spoke.
Okay. So some function that like evaluates to true or false, so has like a return value of bool, is
Yes.
applied to a list, and then whatever it evaluates to true on gets returned.
Yes.
Yeah.
Okay, so let's write signature for this. So you're saying my filter, the name is suggestive. Let's say it takes what I'm going to call a predicates. And it takes a list. And now predicates is supposed to take something. Well, let's put a type variable. Okay, but you were right. It should return a Boolean. That's an important part of it. And the second thing that it takes is a list. And what does it return? The type of what it returns.
It returns a list.
Right. And now returns. Now what's the mathematical description of what it returns?
The list of elements for which pred evaluates to true.
The elements of what?
Of the original list.
Which is called?
What is it called here? LST?
On which pred gives what?
True.
Good. Perfect. Yeah, exactly. And okay, but now what is its signature? What do I fill in for all 3 of these positions?
Well, whatever is going to be in like the thing, yeah, whatever is going to be in the first place there in pred, that goes into pred, that has to be the type of the list.
Sure, but what do I write? What do I write?
A, B,
Yes.
C.
Well,
And then
what's the second one?
A, list of type A.
Yes.
And I guess you'd have to return a list of type A as well, yeah.
Yeah. So that is the signature of the function. So we can abstract this thing away. And what it really did is that it took the list and it pruned away elements, and it left you only with the elements that satisfied a certain condition. Here, there was big and then there was number. And big and number were both things that really went into constituting this test. And so if we abstract away both big and number and this block right here, we can just take this function, its implementation, and we can paste it here. And then how do I change the implementation? So what do I check? Oh, anyone else? Another person. Does anyone have any questions?
I actually kind of got lost on the my filter.
Sorry, say that again. More specifically.
The concept. What are we
Okay.
trying to do with my filter? I'm sorry.
Yes, good. No, good. Yes, good question. Right. So let's think about threshold big, right? Threshold big took a list of numbers, and it also took a number, and it had the word big in its name. And what did it do? Well, what it returned was all of those numbers in list that were greater than this given parameter or number, right? So number was just a parameter that stuck along for the ride. In fact, I could even specialize it further. Let's say I considered instead threshold 0, bigger than 0. So here's a very long name. Returns a list with only those that are greater than 0. Right? And now I need to change the name as well. So here's sort of an unabstracted version in which this function takes a list of elements and it returns those elements in the original list that are greater than 0, right? Does that make sense?
Okay.
And so what does it do? Well, at every stage, it checks whether the first element is bigger than 0. If it is, then it survives. And we cons it onto the a recursive call. And if it doesn't, we throw it away, right?
Yes.
So now take this we pose the question, is the number bigger than 0, right? So now we are going to abstract away that question. Oh, by the way, the signature of this function doesn't have number, so I remove that parameter. So now it just takes a list of numbers and it returns a list of numbers, right? That's the signature of those bigger than 0, right? Now, I guess I want to satisfy, what I'm really writing is now those satisfying pred, where pred is this argument.
A question.
Yes.
So in the previous definitions, we used greater than something. And
yes.
Yeah, that function takes 2 values, right?
Yes. But
So,
here the second value is num. Here really the second value is already fixed. Go ahead.
So it's fixed, but in the signature we write the function to be a, and it gives a Boolean value.
Yes.
But that a, does that imply that the 2 inputs should be the same type, or something?
Well, so look at the signature. It only takes a predicate and a list, right? Okay, so that predicate has to apply to elements of that type of list. If you take a function that's like greater than 0 and you apply it to strings, you'll get an error, a type error when the program's running, right?
Okay.
Because this only applies to
Um,
numbers.
Okay. So we would switch in this definition of my filter, we would switch greater than with pred.
So what do I replace this with? So I'm going to delete this. What do I put here?
If pred first of the list,
Then if yes, then it survives.
Yeah.
But okay, what's the recursive call?
then my first of the list and my filter.
And then
My
what's the
filter
second?
rest of the list. Yeah.
No, you're missing something.
No? I'm missing something. Pred.
Yes.
I'm missing that. Yeah.
Yes. So pred just goes along for the ride.
Yeah. And if that doesn't happen, if that doesn't,
Then you just return this, right?
Yeah.
There we are. Martine, did you understand this?
Yes.
Okay, so yes. So what's being abstracted away here is really this test. Here, the test was greater than whatever the thing is 0, right? Here, but now we've abstracted that away to just be pred. Now, because it's being used on an if statement, this better evaluate to a Boolean. If it evaluates to anything that's not a Boolean, we're going to be in trouble. So that's why we say the type should, really, we don't care about what the type is. The only thing that matters about the type of the input is that it should match, it should make sense on elements of the list. So if you have a function that takes numbers to Booleans and you give it a list of numbers, then that checks out. And what it'll return is a list of numbers. So let's do a few tests. Let's say we're going to call my filter, and let's say we want to test greater than 0, right? How do I write a greater than 0 as a test that uses only, as a function that only takes a single parameter?
Using a lambda,
Good. So I say lambda. Okay, what's the parameter called?
call it x,
Sure. Then what do I do?
parentheses greater x0.
Yes. So this is one of the reasons that lambdas are really useful. I've now constructed a predicate as a lambda. Okay, and let's say I want to filter that on some list. What has to be in the list? What type of things?
Numbers.
Good. So -2 is a number, 0 is a number, 1 is a number, right? And then if I just run this, it'll give me list 1. 1 is the only one of these 3 numbers that's bigger than 0, right? I can also like explicitly run it here. And of course, this function is implemented in the library and its name is filter. Built in. And the name, it works. It filters. Well, it filters. It filters the list for those elements satisfying pred. Discards everything else. So the name is fitting. And now I'd like to do the last thing for, okay, last thing or second last thing for today. I'm going to answer Martine's question from way back when about what is the relationship between lambdas, first class functions, and recursion, specifically structural recursion. So by the way, these things are called higher order functions. Functions that take functions. Oh, let me give another example. That's take or return are called higher order. And that name comes from logic. There's something called first order logic and there's something called higher order logic. And the difference between one and the other is basically the difference between first order programming, where you just have data and functions can't be data, and there's a distinction between functions and data, and higher order logic, where functions can be data. And that distinction is the same as first order logic and higher order logic. And in this class, actually starting from tomorrow, we'll start studying logic. Now, it won't be obvious what type of logic we're studying when we're doing proposition logic, but when we get to predicate logic, we'll be studying higher order predicate logic. Okay, that apart. First order and higher order logic. And it's called higher order because it makes sense to talk about, for example, second order logic, third order logic, and then higher order logic is really infinite order logic. Anyway, okay, that's a digression. Functions can also return functions. Let's say add builder. So we have the function add1, for example, right? But if we try to do something like add2, then that doesn't exist. And one way that I can put all of those together is that I can define, let's say add builder. It takes a number, and what does it return?
A lambda function.
Let's say x, and what does it do?
Plus x n.
So, right. So let's look at its signature. So it takes a number, right? That's for sure. And what does it return?
A function?
Yes, what does the function take and return?
The function that takes a number and returns a number.
So functions can return functions, and those functions can be of a certain type, right?
Yeah.
And now you see that brackets matter. For example, node brackets matter. This signature is not the same as the signature had I put parentheses around the other way, because then that would be a function that takes a number and applies a number. Anyway, and what does it do? It takes a number, returns a function that increments its arguments by n, right? That's a description of what it does. And so, for example, add builder 1 is the same as plus add 1. Now, if you tested them for equality, Actually, that's a really interesting question. What would happen if I tested them for equality? So at the end of the class, when we test these things for equality, it'll actually succeed. But it'll probably fail right at this stage. I know that it'll fail. It'll 100% chance fail. It'll say false. Equal, not equals. It'll say false. But really, the functions do the same thing. So if I do, for example, add builder 1, which returns a function, and I do that to 3, it'll give me 4. So no matter what argument I apply to add builder, it's going to be the same as had I applied add 1 to that argument. By the way, to make a distinction, consider, let's say, apply to 0. Which takes a function from numbers to numbers, and it returns a number. So it just returns f of 0. Applies f to 0. Notice that this function signature is rather distinct from this function signature. So parentheses in signature, or let's say bracketing in the signature matters. As with these examples. Okay, going back to there. What is the relationship between higher order functions and structural recursion? So the answer is that we had 2 higher order functions. We had filter and we had map. There's a third higher order function that basically accomplishes the goal of structural recursion. And that function is called folds, foldr. Structural recursion on lists. And it is a very important function for this reason. If you use it, you can eliminate all recursion. You can eliminate all list recursion. And let's say explicits. When it's that's structurally recursive. Now, to motivate this, consider our function SUMList. Do I have SUMList defined at the top of the page? I don't. Sum. So what was the structurally recursive definition of SUMList? Let's build it up. Okay, what do I do to write a structurally recursive list function?
Count and see if it's an empty list.
Templates. Okay, let's not write out the full template this time. We've done it ad nauseum to this lecture. What's the result in empty?
It will be the list itself.
For some list?
Actually 0.
Right. So, and how would you know that? Remember what the signature of some list is. What does some list take? A list of what?
List of number.
And it
And
returns what?
returns a number.
Right. So for example, having the signature would prevent you from accidentally writing the empty list, because the empty list is definitely not a number. Okay. And then otherwise, what does it do? The actual implementation of some list.
Plus the first of the list and some list, rest of the list.
Yep. Okay, so yeah, this is the same definition that we had before. Now we're going to abstract away from this, the structural recursion. So what was, like, think about the proof template for structural induction. Structural induction for NATS. Structural induction transformed a logical statement of the form, let's say for all NATS and P of n into two statements. The first was P of z, and the second was for all NATS k. P of k implies P of s of k. And similarly, if we look at, okay, well, I'll actually tell you what this principle is for lists. Actually, I'm going to assign homework. That's several homeworks this week. I'll send you an email. Please check your email about the homeworks. If you wait until Wednesday to look at them, you'll lose a lot of time. So let's say for all list A, LST, to prove a statement of this form, where A is a type variable, it really transforms it into two statements. The statement for the empty list and the statement that for all list A, LST, and for all A's X. I put the S's here. That P of LST implies P of cons X LST. Okay, so this is structural induction for list A. That's the proof technique. Okay, well, structural recursion as a technique for defining functions is similar. You're trying to define, you're not trying to prove a statement, you're trying to define what some list is for all lists of numbers. And then if you use the technique of writing a structurally recursive function, it changes the goal into writing two different functions. The first is what the output should be when applied to the empty list. And the second is some process that goes from one input to the other input, right? Oh. Yeah. So let's abstract that. So let's leave the signature there, and let's leave the description there itself. We're going to take this and we're going to try and abstract it. So I'm going to call it my folder. And then we don't know how many parameters it needs. Okay, so first off, if the list is empty, then what do I return? By the way, we don't know what the parameters are, so we're trying to determine what the parameters are. If the list is empty, what do I return? Well, I need to return something, right? So let's call that a parameter. Let's maybe call this base. Right? So folder is going to take a parameter. And now what happens here? Well, we have sum list, rest list, and we have first list, right? And I said that you need some way of combining them. Well, how do you combine them? How should I combine them? What should I put here?
A function?
Yep. So in other words, what is my folder? My folder is an abstraction of the templates for writing structurally recursive functions, except instead of sum lists, it's now going to call my folder. And the two new parameters that we added are non-accumulator parameters that just go along for the ride. Whoops. So we have abstracted the idea of the template of writing a structurally recursive function into a function.
Question.
Yes.
Doesn't this like repeat the empty list base thing unnecessarily all over the place though? Because like the previous
Well,
template
I
we did.
mean, this will, so to answer your question, if you're worried about functions going along for the ride, then read about something called tail recursion.
Okay.
So them going along for the ride, it doesn't keep making copies of it, actually. But that's not the only reason. No, this function is not strictly speaking tail recursive. Okay, the actual memory model that Racket uses, it won't create copies of things over and over again. So don't worry about efficiency. Also, we're not worried about efficiency. Okay, anyway, this function is not tail recursive. Sorry, ignore what I said about tail recursion.
No, I didn't mean
but
it as tail recursion, but like what I was asking, like what I'm asking is like over here, right? When in the template we defined earlier, we only really like had the idea of like an empty, like once, you know, right? And then like in the no, we didn't. That's just me being dumb. Never mind.
Okay. Right. So what we had is that when it's empty something, we return something. Otherwise, we combine the recursive call with the first element of the list. And these two together should produce the answer. Right. So here we have just taken that and we have just abstracted that into a function. Let me just quickly check whether I have the order of the functions right relative to the way that it's defined in Racket. Where is... Okay, what is it? Yeah, okay, that's the right signature. Yes, that is the right signature. And I want, how am I going to combine the functions? The combining function is Oh, that's how it combines it? Okay, so these guys should go first. Okay, for no reason whatsoever, I'm going to make first list be the second argument. No, actually it was right before it. No, and I see why it would be less efficient. Okay, first list is the first argument. Okay, yes. So for let's just look at this. So when we wrote sum list, then okay, let's define it like this. If we just abstract away the solutions to the problem of writing a structurally recursive list function, what is, let's say, what is the base case? What is the base case for sum list?
0.
And what do I use to combine them?
Plus.
Yes. So plus is a function that takes 2 arguments. And if you look at func here and you look at plus here, I can literally replace func with plus. So I can write fold_r without explicit recursion. My fold_r is still recursive, but any function that can be written using structural recursion on lists can be written in terms of fold_r. So for example, I can do my fold_r let's say sum list 2. Bam. Okay, here comes the fun part. Okay, what does my fold_r do? Well, okay, so at a very high level, this is a high level description. Performs, evaluates a structurally recursive function definition. Structurally. Okay, let's leave it at that high level description for now. But okay, here's the interesting part. What is its contract? By the way, let's to do an example. What is the contract of plus? Plus, I'll write a colon after plus to say what its contract is. Plus, what's the contract of plus?
It takes in 2 numbers and returns another number.
Yep. What is the contract of 0? Or what is its type? Okay, and what is the type of list in this case when applied correctly?
A list of numbers.
Okay, with that in mind, and how we wrote my fold_r, let's figure out what the contract of my fold_r is. So what's the first thing that it takes? Func. How many parameters should func take?
2.
Yes. So let's just write. Let's put underscores for the moment. And then it returns something. So we have to fill those in. Okay. Then it takes a second parameter. And then it also takes a third parameter. What can we say about the third parameter?
It's a list of some parameter.
Yes. And then what's the output? Okay, let's say just leave it as this. So okay, let's say that it takes a list of type A. So I'm just going to put that type variable here. So if we take if list has type A, what type does first list have?
A.
So yeah, notice this. If we know that lists, I'm going to use this colon. I'm starting to use this colon this class, but starting next week, you'll come to love or hate the colon. If we know that list has type list number, then we can say that first LST, if it doesn't throw an error, is a number. So, okay, if list is a list of type A, then what is the type of first list?
A.
So func, what should the type of its first parameter be?
A.
Okay. Now, what the second parameter is going to be a call to my folder, right? The second parameter is this. Now, one of the things that can return in the empty case is base. So let's say that base has type B. Well, if base has type B, then it might be returned by my folder. So the second argument has type what? Oh, okay, actually, sorry, let me fix that. Let's put it like this way. Let's suppose that base has type B, right? As a result, what type does my folder return? So now we'd like to fill in this position. Sorry, we'd like to fill in this position. We'd like to say what type my folder returns. It returns base. Base has type B in one of the cases. So overall, it returns something of type what?
B.
B. So yeah, that's the correct way to fill it out. First, we fill in this. That forces our hand here. Then we choose the letter B here. But if we chooses here, then we see if the function should return something of a single type in either case, then that type better be B. But then if we go here and we see that to func, we applied first to an argument of type A and then to an argument of type what?
Also B.
And its return type should be the same as the overall function, right? And that's
B.
B. So here is the signature written in a parameterized way, abstracted with types abstracted with type variables for the Foldar function. And in the library, this is Foldar. This is built in as Foldar.
A question, can you explain why it has to return B again, like the last step?
Right. So the way that we developed this contract, how we worked out this contract. So first we started with everything unknown. Then we said, let's just fill this in with A. then since that's filled in with A, first list takes this parameter, so func as its first argument should take something of type A. Okay, then we couldn't infer anything else, and so then we just arbitrarily put a B here. But this is what's returned from the function overall, because that's the argument for base, and base might be one of the things that's returned. Now, no matter which one of these two cases happens, the result should be of a single type. So because in one of the cases it returns something of type B because it just returns base, then the overall return type should be B. Then since the overall return type is B, we can look at this position here. And since that's a call to my folder, that returns B. So the second arguments to func should be of type B. And at the same time, that's what's returned overall. And this is sort of like a type inference process, which is what we'll study starting next week. Well, we'll study this week. We'll study this starting tomorrow.
You mean Wednesday? The day after tomorrow?
Sorry, say that again? Oh, I mean, yeah, Wednesday. Study this. And so as an example, then using the built-in library, I could write folder, let's say +0, and then the list. And that sums the numbers in the list using the built-in folder function. So this is a really cool thing about functional programming languages. All functional programming languages will have these three functions built in. They're the building blocks of almost everything: map, filter, and folder. The R stands for write. I won't talk about foldel. Actually, foldel, I'll just say this one thing, is to folder as structural recursion, sorry, fold R is to foldel. Structural recursion is to a recursion with an accumulator. Is to structural recursion on lists. On lists is a very important thing. This folder has to do with lists, right? Its signature has lists in it. Is to recursion on lists with an accumulator. Let's say I'll start a new line here. Structural recursion on lists is to recursion on lists using accumulator. So the definition of plus, that's, I won't define what foldel is, but this will now do the accumulative definition. It'll perform this computation as an accumulator. But don't worry about foldel. But folder is important. And remember, okay, and then we also learned about lambdas. So that was a lot of material for today.
Wait, question. Sure.
Hmm?
This is reduced, right?
So, Reduced in the sense that lambdas will be values?
No,
Oh,
listen, this
okay.
is like
Sorry,
this is
go
what's
ahead.
called reduce in like other languages, right?
Map and reduce. So Google's like, I think reduce the same as a folds. Reduce might be apply. I think reduce might be apply. No, reduce is folds. Yes, this is reduce. Either of these are reduce, I guess. Possibly. It's ambiguous as well because it turns out that in rackets, you can also add multiple numbers together. And so there's another way to do this. You can apply plus to its list of arguments. So reduce typically means probably foldar, but here are 3 different ways that we can reduce it. So the apply is another higher order function. If a function takes multiple arguments, then you can take apply, the function, and a list of arguments, and then it'll apply the function to each of those arguments separately. It's actually impossible to write apply on your own using what we've done so far. But there are several other built-in functions that can be used to write apply, which I haven't discussed. Oh, let me say one more thing. This is the final thing. Define a function on arguments. Let's say arg1. Let's say body of the function, where the body of the function might occur used there, is actually shorthand for define func as what? So so here I'm defining a function. I'm making the name mean a function. But let's say I just want to define the name to be something. Then what is the name going to be bound to?
A lambda?
Yes. Now lambdas can take multiple arguments. So you can type in arg1, arg2 with the body. In fact, here's the really cool thing. Now that when you switch to intermediate student language, let's look at what happens in the stepper. So there's going to be a lot in the stepper because we've written a bunch. Actually, it's going to evaluate each definition one by one. I'm now going to share the stepper. Oh God. Oh, that does not look nice. Okay, there are a bunch of definition. Yeah, no, this isn't going to happen. I'm going to open a new tab and I'm going to write something very small. Let's just consider define square x. Oh, do you see my screen? You don't see my screen right now.
Don't see it.
Do you see it now?
Yes.
Okay, so let's just say define square x times xx. And then let's say square 2, 3. And let's put it through the stepper. So the stepper will still have the function definition as it usually appears. Do you see the stepper now?
Yeah.
Okay, but instead of actually evaluating the function body as it did before, it'll replace the function body with a lambda. So there you see that square. Square is really a name that's being defined as a lambda. Defined definition is really shorthand for defining square to be a lambda. Now remember how we saw that if you had function definitions and I wrote something like 2 + 2 in the function definition, that it wouldn't get reduced. So function definitions, if there are things that you can compute in them, they're not computed when you define the function. Why is that? It's because functions are defined to be lambdas, and lambdas are values. So you don't try and compute any further. So really, when you switch to ISL, and this is the way that Racket will work from now on, definitions are just shorthands for defining the names to be lambdas. And then when you have a function application, it'll look up the definition, it'll replace it with a lambda in the same way that it would look up a data definition that's not a function. But now you can't say that because, well, now you just say functions are data. So it's just a data lookup. Then it takes that lambda and then it substitutes. How are lambda function applications to lambdas evaluated? They're evaluated by substituting the parameters in for the variables in the body. Whoops. Then you substitute and then you compute 9. And then that's that. Okay, I'll send you an email about homework. Do you have any questions? So for the exam, the first hour of today's lecture was the most important thing about programming that you have to know. That was me trying to lay out as plainly as possible and as explicitly as possible how you think through writing recursive functions on lists by structural recursion. And I expect everyone to complete all of their homework and get caught up. You have to get caught up with your homework before the exam. What you're supposed to learn is the problem solving strategies that are relevant here. And I'll also assign another proof problem. And then it'll be more of the same as before. So on the exam, you'll be doing exactly the same thing, but the problems will be completely new. But you'll be thinking through them in this way. Okay, go ahead. Question, right? Sorry, do you have a question? Okay, well, I think that's that. I went over time, but hopefully it was worth it. Was today's lecture enjoyable?
Yeah.
It was enlightening.
There was a lot of new things that I put forward. So this was the all of higher order functions in a single lecture. And type variables. And this process of abstracting. So I actually like this level of exposition. I read this from a book called How to Design Programs. Okay, see you on Wednesday and check your email. Bye.
Bye.
Bye.